Greetings everyone, I'm Triet, a researcher from Croft at the University of Adelaide. Welcome to the presentation of our paper, PUMiner Mining Security Posts from Developer Question and Answer Websites with PU Learning, accepted in MSR conference this year. This work has been partially funded by Cybersecurity CRC. In this work, we propose an effective and robust method to perform large-scale mining of security content from question and answer websites. I know it's a pity that we cannot meet in person during this difficult time. However, I'm still looking forward to a fruitful follow-up discussion of this virtual presentation. Nowadays, many open source threat intelligence databases provide information definition about secure vulnerabilities and secure coding practices so that we can prevent future security threats. Good thing about these sources is that the information has been verified by security experts. On the downside, such a meticulous checking process may result in a long delay, sometimes even months. Such delayed updates can even lead to obsolete solutions. For example, on CWE, MySQL real escape string is recommended for protecting PHP code against SQL injection. However, this function has been deprecated and suggestion to be replaced in the official PHP manual. It's also not easy for these sources to cover all the security issues for a wide spectrum of technologies and programming languages. And these needs led to the emergence of technical question and answer sites like Stack Overflow, Security Stack Exchange, where the knowledge can be updated much faster through crowdsourcing with millions of users and developers on a daily basis. Here's an example post on Stack Overflow recommending updated functions for mitigating SQL injection in PHP. A post typically has a title, a question, answers, and tags, which would be utilized for retrieving security-related content. As mentioned, this work aims to devise an effective and robust method to mine security intelligence from Stack Overflow and Security Stack Exchange. There are two traditional approaches to this task. The first one is keyword matching. That is simple and fast. However, it relies heavily on domain expertise to define relevant keywords. Also not easy to balance between precision and recall of the retrieval. So specifically, few keywords may neglect many related posts. Some keywords may even have multiple meanings, which can affect the relevance of the retrieved post as well. For example, attack is a common security word, but also often means approaching a problem in general context. Another method to overcome difficulty of keyword matching is using NLP techniques to extract important text features automatically, and then applying machine learning, deep learning to classify whether a post is related to security or not. However, we still need a good dataset containing both security and non-security posts for traditional binary classifier to work properly. It's also not easy to obtain negative samples in this case, since again, it depends on how well we define security context. To address the dilemma between these two methods, we reformulate this problem as positive unlabeled learning and propose PUMiner to solve it. Intuitively, we can first use keyword matching to obtain a good but not complete set of security posts. Then through PU learning, we can leverage both the patterns in the positive set and the latent information about the negative class in the unlabeled data to build a classification model. Within the PUMiner framework, we have three main processes: model selection, model building, and prediction. Starting with the model selection, we first pre-process posts to reduce noise for a learning process later on. We apply standard techniques like removing HTML tags, code snippets, and stub words. We also perform low case conversion and stemming. After that, we generate PU datasets that contain both security and unlabeled posts. And the first part of datasets goes into the stratified K4 cross-validation process. Here we choose K to be 10, and stratification helps to maintain the data proportion in this fold. In this validation process, there are two main tasks. First, extracting feature embeddings of posts, and then applying two-stage PU learning algorithm to build a security classification model. We repeat the same procedure k times to select the model configuration with the highest performance for the next process. Moving on to the model building, we use the same two steps with the optimal configuration above to train a complete PU model. Finally, in the prediction process, we load both the feature and PU models to predict whether new posts are security related or not. In this work, we develop heuristics based on both the tags and content of other parts of a post to build a security dataset for PU learning. Regarding the tag-based heuristics, we follow a standard procedure in existing works, where we first obtain the anchor and co-occurring tags within the security context. We then employ two metrics to quantify how much a tag is related to security and how popular it is. After that, we filter them using the tag thresholds to select the relevant set tag. Moving on to the content-based heuristics, we start with the remaining posts after excluding set tag. Then we prepare 234 security words to check the security content of the post. Intuitively, we want to make sure the security words in the post are first prevalent with keyword ratio, and at the same time diverse enough with keyword count. With these content thresholds, we obtain the set content and then combine it with the set tag to build the golden security dataset for training our PU model. In this slide, I will describe the context-aware two-stage PU learning process. First, we extract the post ID tags as well as title, question, and answers of a post to train a Doc2Vec embedding model. Doc2Vec is an extension of Word2Vec in which the context of metadata that are post ID and tags in this case also learned with respect to the words in other parts using one hidden layer neural network. After this process, we obtain the feature embeddings where similar content and post stay close to each other in the embedding space. Next is the two-stage PU method that extracts non-security posts from the unlabeled set by contrasting their features with the security ones. Accordingly, we can transform this problem back to a traditional binary classification. In stage 1, we first use the embedding features to determine the security and unlabeled centroids. Centroid can be seen as a representative post of a whole set. Here, most of the unlabeled posts are non-security, so the unlabeled centroid can approximate the negative class quite well, and we've demonstrated this indeed the case in our experiments. After that, we compute the cosine distance from each unlabeled post to these two centroids. If a post is closer to the unlabeled centroid, it will be added as a reliable negative. We also add a learnable coefficient alpha here to make our model more flexible. Finally, we combine the security and reliable negative post to create a dataset for training a binary classifier in stage 2 to determine the security relevance of a post. Next, we propose 3 research questions to evaluate PUMiner. First, we want to explore which model configuration of PUMiner is the most effective for mining security intelligence from Q&A sites. Then we compare the optimal PUMiner with existing methods on this task. Finally, we investigate how PUMiner performs with respect to different sources and sizes. To set up our experiments, we have PU and manually labeled datasets. We extract 90% of such PU data for training and validation, and the remaining 10% is for testing, namely test depth. Besides test depth, we also have manually labeled test norm and test hard to evaluate PUMiner explicitly using both positive and negative labels. Test hard is designed specifically so that the keyword matching heuristics presented earlier would all fail. We also investigate 6 popular machine learning classifiers for the second stage of our PU model. The first 3 are single models and the other 3 are ensemble ones. We also employ a wide range of evaluation metrics for both PU and label datasets, including precision, recall, F1 score, G-mean, and Matthews correlation coefficient, namely MCC. G-mean is used to select the optimal model since it has explicit formulas for both PU and label scenarios, where MCC only works on fully labeled datasets since it requires the negative class. Now I'll present our main findings. In research question 1, we first observed that the doc2vec feature embeddings clearly help to distinguish security from negative posts. The visualization of unlabeled posts here indicates that this set mostly contain negative posts, supporting our decision to approximate the negative class with the unlabeled centroid. Next, we find that the XGBoost model obtained the highest G mean overall. Moreover, every model configuration achieved at least 85% G mean, which is quite promising for this task. On average, ensemble models also outperformed single counterparts. Another point to note is that when alpha in the stage 1 of our model increased, it also increased precision, yet lowered recall. On average, alpha larger or equal to 1 produced more stable performance. In research question 2, we use the optimal model of PUMiner in research question 1 to compare with existing methods. And we find that PUMiner outperformed these methods by a significant margin, demonstrating the usefulness of unlabeled data to the learning process. Our two-stage model was also better than one-stage model, showing the necessity of both PU stages. PUMiner also performed reasonably well on test hard with 75% MCC, where keyword matching totally failed. In research question 3, we want to test how PUMiner reacts to changes in the data source and data size. Firstly, all the retrieved security datasets on Stack Overflow and Security Stack Exchange helped PUMiner to improve its performance. Interestingly, Stack Overflow supported the normal cases better, while Security Stack Exchange gave more predictive performance to the harder cases. This might be because Security Stack Exchange was less formal and not refined by our keyword matching heuristics. Thus, it can cover more extreme cases with less explicit security context. Another important finding here is that PUMiner was significantly and consistently better than a supervised model that treats all the unlabeled data as negatives with respect to different positive ratios. In an extreme dataset with only 1% of security posts, PUMiner still obtained nearly 80% MCC for the normal cases. Here are some key takeaways of our work. We're the first one to formulate the security retrieval from Q&A sites as PU learning. Then we propose PUMiner Framework to solve this problem. We demonstrate that PUMiner obtained promising results and significantly outperformed existing models even with large unlabeled data and limited positive samples. These results have shown that utilizing unlabeled data with two-stage PU learning is a promising direction for reducing labeling effort of information retrieval in software engineering. Last but not least, with PUMiner, we obtained and released to the community the largest security dataset on Q&A sites that can stimulate further research in the area of secure software engineering. Regarding the future directions, it's interesting to study how PUMiner would help in retrieving data in other domains, and more than 170 sites on Stack Exchange would be a good place to start. Regarding PUMiner itself, you can try to further enhance its performance by incorporating security knowledge bases, improving the first stage, or just simplifying the whole PU learning process. This also concludes our paper presentation. Thank you very much for your listening. You can scan this QR code to read the preprint of our paper. If you have any questions, please feel free to share it with me via my email here or during my paper section at MSR on June 30th. Until then, keep safe and keep your software safe.